All right, let's do our third day of thermochemistry unit, thermochemical equations. Now, in my opinion, the most difficult part is knowing the signs as that you need to put on the heat, um, which you'll see what I'm talking about in a moment. But otherwise, it's a pretty simple setup of equations. So after today, I want us to be able to define what a thermochemical equation is and use its information to calculate energy used or produced. This is the negative stuff that I was in positive signs I was telling you about in a chemical reaction. Explain what the delta H of a reaction is, or change in heat, and how it can be found. So a thermochemical equation is just it's like a chemical equation like we learned in chemical reactions. But it gives us a unit of heat after it or in it. Every reaction has an energy change associated. So this enthalpy is heat content of a substance at constant pressure. So what that will mean is that a chemical reaction is going to occur, and it doesn't mean that there's going to be heat created, but it's a heat of a reaction. So it could be absorbed or released. So it could get hot or cold, or like we learned in the last lesson, it could be endothermic or exothermic during the chemical reaction. So when we do a delta H, it indicates a change in enthalpy. All right, so here are the two chemical reactions. It could be shown two ways. So the first way is the chemical reaction, and then after it, it'll give you this heat, or delta H, okay, a change in heat. And so a negative sign means that the reaction is exothermic, so it is getting rid of heat, it is releasing heat. So that means the heat of the actual reaction is the reaction is losing heat. That's why it's a negative sign. Even though when you feel the beaker and it's getting hot, you feel like it should be a positive sign. However, the actual reaction, it's losing heat to the environment, which is what you're feeling. So heat is a product. So you're going to add heat after the product. So two ways you could have written that these two react to make this, and it got hot. Okay, so there are two ways that you can write that. You can write it the reaction separately, and then delta H is this is how much energy it lost. Or you could write the energy into the problem. So for example, you combine methane and oxygen, and it creates carbon dioxide, water, and heat. Okay, so you could write it as a product, or you can write it separate from the equation. You'll see it both ways on the assessments, and so just know that, okay, if it has a negative sign here, it's on the products. Now, if it had a positive sign, okay, that means it was in the reactants, okay? So that means maybe it got colder. So for example, if this chemical reaction were to take place and you felt the beaker and it got cold, that means the environment lost heat and the reaction gained heat, okay? So a positive sign means that it gained heat. So here in the reactant, it gained heat. Or maybe it needed heat to start or whatever. So energy is a reactant, and it's endothermic. So this type of reaction actually feels kind of cold. Okay, so the heat of a reaction is the amount of energy used or produced when the coefficient equals the number of moles in a reaction. So this is a new conversion factor. So yes, we're using dimensional analysis for this too. Dimensional analysis, that's why I did a mini unit at the beginning of the year. It's in everything. So for an example, so here's a type of equation where you have an equation, but separately they tell you the whole heat situation, which is actually the equation we saw just a while ago, which means carbon and sulfur combine to make carbon disulfide, I guess. And the heat of the reaction, it actually got colder. It's endothermic. The positive sign indicates that it's actually in the reactants. So the question says how much energy is needed. So that's our unknown when 1.27 moles of sulfur reacts with excess carbon. So our known is this number, okay? We know how to find our known and unknown, right? The unknown says how much energy is needed. We use these units right here. And we have our known and unknown. So in the reaction, we're going to use this and this only. We don't really care about the others. It's kind of like the limiting reactant, but not really yet. So we write our known here, and then we're just going to do a conversion, okay? So moles of sulfur is here, so that means moles of sulfur should go here. So we're looking at the equation to find this ratio, all right? So the moles of sulfur should be 2 down here, and then the heat will be 89.3 kilojoules, okay? The question... the difficulty that I find is this positive or negative sign. In this case, it's easy because you think that they correlate with each other. However, it's not always that simple. So you would take in your calculator 1.27 times 89.3 divided by 2, and you have your answer. So that's how much energy is needed when that much sulfur reacts with carbon. Sorry, so needed would mean the plus sign. So if you are absorbing, or if you need it in the reactant, it's going to be positive. If you need it in the product, if it says produced or emitted or whatever, then it's going to be in the product side and it'll be negative. All right, so next example, how many moles of water would be produced if this reaction gave off this much energy? So in this case, the heat is part of the equation. It's not separately. If it was separately, it would say delta H equals negative 890.4. So it says how many moles of water, that's our unknown, and then our known is this, 347.1 kilojoules of energy. So it gave us this. The fact that it was given off or left the system, that's why it is negative, okay? So the gave off, produced, radiated out, whatever. If it's leaving the system, which is the experiment, if it's leaving it, if it feels warm, it's negative. And then the unknown is how many moles of water. So then we just look at our equation, and we're only dealing with water and the heat, okay? So our known will be negative 347.1. So kilojoules. So kilojoules will be down here. So it'll be 890.4 kilojoules, okay? And again, we're dealing with gave off. It's going to be negative. And then you have, so this is how much energy is released when you have 2 moles reacting of water, okay? So the kilojoules cancel, and you will have this many moles of H2O. So the negatives are coming from the equation. You're just going to have to know if it says needed or required, that means it's positive. So that means it's going to be over here. If it says given off or produced, it's going to be over here. It'll be negative. All right, how much energy is produced? There you go. Produced, that means it's going to be negative. It's going to be created and going away. How much energy is produced when this much, that's our known, of oxygen reacts with excess ethanol? So our known is that much oxygen. It's asking for how much energy is produced, so that's our question. And then we're only dealing with oxygen and the heat, okay? So we're going to set up our problem. So 75 is our known. And then we need to put grams of oxygen down here, okay? So we're going to grab that off of the periodic table, and we have to convert it to moles, okay? Because we can't really talk about heat without moles, because you don't see like so many grams of oxygen. These are moles. So if we have grams, we have to convert to moles. So grams, we'll grab it from the periodic table, and then we'll have moles up here, okay? So that's just a simple conversion factor we've done since the beginning of school. Then we need to put moles down here, and we need to do our heat. So we'll have moles, so we look at the coefficients. So it'll be 3 moles of oxygen, okay? And then it says produced, so it's going to have to be negative, okay? So that produced, given off, gone away from the system, it's a negative, okay? And then the moles of oxygen will cancel, and we will have our answer. So again, the word produced, that's why it's going to be negative. All right, let's do number 6 on the homework problem today. How many kilojoules of heat are produced when 34.0 grams of iron oxide reacts with an excess of carbon monoxide according to the following reaction? So it gives us a reaction and it gives us our delta H. So we just need to find our known and our unknown. Okay, so it says our known is 34.0 grams of iron oxide, Fe2O3. Our unknown is how many kilojoules of heat are produced. So we're looking at our heat and we're looking at iron oxide. So we always start with our known, which is 34.0 grams of Fe2O3. And since we have grams, we need to convert to moles because we can't talk about the ratio unless we have our stuff converted to moles. So for every 1 mole of iron oxide, it's going to weigh a certain amount, and we're going to have to add that. So that means we would have iron, we have 2 of them, and iron will weigh if it is somewhere around here, and I am like losing my mind. There it is. Sorry, somebody was knocking on the door and it was distracting me. 55.845. So we have 55.845. And then we have oxygen, which we have 3 of them, and that's 15.999. We'll add that, and that will be our how much that'll weigh per mole. So I'm going to find out how much that weighs. So 2 times 55.845 plus 3 times 15.999. So the answer will be 159.687 will be our molar mass. Okay, so we have now we're at moles of iron oxide, and we need moles because we can't talk about heat unless we have moles to convert. So for every, this is a 1 here, so for every 1 mole of Fe2O3, if it was asking us for something else other than iron oxide, like this one, this number would have been 3. Okay, so we got the 1 from here. It's not a conversion factor from like normal. This is a ratio from the equation, so it just happens to be that it's 1 here. So for every 1 mole, we have negative 26.3 kilojoules. Okay, so for every 1 mole we have that. That's produced, so the produced is why it's negative. Okay, so we just type that into the calculator because we are at our units of unknown. So we would do 34 divided by 159.687 times, I'm not going to type the negative because you just know it's going to be negative if you're multiplying by something negative. If you don't know that, you can put the negative. So we have 3 significant figures here, so 5.60 is what we will write. Kilojoules. And don't forget your sign.